Hi, Integrated Math 1. Welcome to lesson 5.2.5, where we're going to discuss reflectional and rotational symmetry. So we've talked about reflections before, how they're just flipped. We've talked about rotations before, how we turn things. But this is a little different. It's actually a little easier. We're going to talk about symmetry, which is just a little bit different. Similar ideas, but a little different. So our goals today, we're going to identify geometric figures with what we call line symmetry, reflectional symmetry, and rotational symmetry. We're going to identify lines of symmetry for different geometric figures. We're going to describe rotations that can carry a figure onto itself. And we're going to describe reflections that can carry a figure onto itself, right? So our key terms today are going to be reflectional symmetry, rotational symmetry. Obviously, that's what we're talking about today. So those are going to be your key terms. You're going to want your workbook and a pencil and probably a straight edge as well, I would recommend. So you have learned that pre-images are congruent to images after rigid motion transformations, right? If it's a rigid motion transformation, it's an isometry. I don't change size, I don't change shape. The original is congruent to the new guy. So how can you use transformations that you can actually take a figure and map it onto itself? That's weird, right? A figure being congruent to itself, but that's what we're going to talk about today. Pardon me. So on page 108 and 5-108, you have several different shapes. Bloop, 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 bloop. I'm not going to make you copy these onto patty paper. If you'd like to, you're welcome to do so. But you can just draw on them right there on the book. Determine whether you can fold the shape in half so that half of the figure lies exactly on the other half of the figure. Like, can you take the figure and fold it and get that butterfly effect, that one half is going to end up sitting right on top of the other half if you fold it? If so, are there other places you can fold to make it do that? Go ahead and play around with these shapes, and instead of folding it, you may just want to draw a line through where you would fold it to make the two sides map onto each other. So hit pause, see what you can find, and then hit play when you're ready to check your work. So I'm looking at this first figure here, and I realize I could draw a line. Like, I could just be like, draw a line like, oh, wait, I need a pen to draw a line. Haha. I could draw a line like right through the middle. And if I folded it on that line, it's not a good line. This side would end up right on top of that side. But it's not the only one. I could fold it this way, or this way, or this way, or this way, or this way. Oh my gosh, so many different ways I can fold it here. This is the pretty version. So many different lines I could fold it along that would make the one side go right on top of the other. You know what, even this weird dude down on the bottom, like I could draw a line right through the middle of that, right? That would make it fold onto itself. I don't think there's anywhere else I could fold it that would make that work though. You know what though, for my star, I could fold a line here or here or here or here. So I have like 5 of them here. That's kind of cool. Ooh, my circle. You know, for my circle, pretty much any line that goes to the middle, right? So I guess for my circle, I have like an infinite number of folds. Oh. Some of these others don't work. Like if I tried to fold corner to corner on this one, these 2 corners wouldn't line up when I fold them. And even this one, my sides are somewhat different length, and so that causes me problems when I go to fold them. Okay, so we did the foldy thing. What if you wanted to rotate them? Can you rotate your figure so that it looks exactly like it did before the rotation? And if so, are there other rotations that could do that? I don't want 360 because if you rotate 360 degrees, you're just right back where you started again, right? They all meet 360. I want to know if you can rotate these a different number of degrees, like 180 or 90 or 60 or 30. Can you rotate it so that it's right back on top of itself? Hit pause, jot down your thoughts, hit play to check your work. So I'm going to start with this hexagon. I realized that I could just like boop, 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 right? It would just be like click, 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 click into place. So there's 6 possible rotations I could do of this hexagon. Of course, the circle has an infinite number of rotations, right? It's a circle. No matter how much I turn it, it's going to be the same circle. Some of the others, let's see. This one, I could rotate twice, right? Be like boom, boom. That would work, right? My star 5 times, right? Boop, boop, boop. But you know what? For my trapezoidy guy here, I would have to go full 360 before I ended up back where I started. And same thing with my triangle. So they're not as useful. So we've kind of been naming these. Can you take a moment and actually name these things so we know what's what? Can you go ahead on page 110? Can you actually name all of these shapes that we were just using? Hit pause, write down the names, and then hit play to check your work. So I'm trying to be as specific as possible. So yes, this first guy is a hexagon, but I see it has all congruent sides, all congruent angles. It's like the perfect hexagon. So I'm going to call it a regular hexagon. Of course, this is a circle. This is a we just skipped over some here, huh? That's not this is an isosceles trapezoid. I have 2 congruent sides, so that's an isosceles trapezoid. I have a parallelogram here. I have a scalene right triangle. I know my picture on the screen isn't very good, but you can probably see in your book that this side is not the same length as that side. So I'm going to say it's a scalene triangle. It's even a right triangle. I can see that's perpendicular there. And of course, I have a star. It's a star. To make you feel good. Let's talk. Reflectional symmetry. A plane figure has a reflectional symmetry if you can draw a line so that the figure to one side of the line is a reflection of the figure on the other side of the line. Sometimes we call it line symmetry, so be aware of that. And of course, we call it line symmetry because we're literally drawing a line that shows that the one side is symmetrical to the other side. Which shapes here have reflectional symmetry? You may want to flip back over to our getting started activity. It'll kind of help you out. So which of these shapes have reflectional symmetry? Hit pause, jot down your thoughts, hit play when you're ready to check your work. So if you go back to the getting started activity, my regular hexagon, I can draw a line through it that would flip, that one side would be a reflection of the other. The circle, I could draw a line through it that one side is a reflection of the other. The isosceles trapezoid, because those 2 sides are congruent, I can draw a line through it that one side is a reflection of the other. And same thing with my star, right? I can draw a line through it that makes one side a reflection of the other. So they can all be folded so that one half of the figure lies exactly on the other half of the figure if you were to fold it on that line. So all of these have reflectional symmetry, sometimes called line symmetry. I have for you an equilateral triangle. It's in your book on page 110. I would like you to consider this equilateral triangle. I'm going to tell you right now that it has 3 lines of symmetry. Can you take a moment to draw all 3 of those lines of symmetry? Hit pause, write it down, hit play to check your work. So I know I have a line through each vertex and out the other side. I've got 3 lines of symmetry. So hopefully your figure ended up looking something like this. What about number 4? How many lines of symmetry does this rectangle have? And explain your reasoning. Hit pause, jot down your thoughts, hit play when you're ready to check your work. So I played with this a little bit and I was like, all right, where could I fold it? And I was like, well, I can fold it here. Not a good line, but you get the idea. I can fold it here. Okay, this is again not my best line. I thought about trying to fold it corner to corner, but I realized that if I folded it corner to corner, that these corners weren't going to line up when I did my fold. They were going to be like off a little bit. So it looks like my rectangle has 2 lines of symmetry. I'm going to erase all this and I'll put the pretty one up. There it is. What about your square? Oh, how many lines of symmetry are there in your square? Draw them in. Tell me how many there are. Hit pause. Draw them in. Tell me how many there are. Just kidding. Wow, I didn't. Okay, yeah. Sorry, I'm giving away the answer. Hit pause. Workout number 5, and then hit play when you're ready to check your work. All right, so clearly I messed up a little bit. My little transition didn't work there. I'll have to adjust that. So a square has 4 lines of symmetry. I can go horizontal and vertical, but then I can also go corner to corner because it's a square. So I hope you got the feel for this reflectional symmetry, like I said, sometimes called line symmetry. A plane figure can also have rotational symmetry. Here's our other key term on page 111. If you can rotate the figure more than 0 degrees, those are supposed to be degree signs. Sorry about that. Wow, I had all kinds of issues. 0 degrees, but less than 360 degrees, and the resulting figure is the same as the original, you have rotational symmetry. I can turn it a certain number of degrees, and it'll end up right on top of itself. It has to be more than 0 and less than 360. So which shapes in our getting started activity have rotational symmetry? Again, you might want to flip back and look at some of the work we did earlier. Hit pause, let me know who has rotational symmetry, and then hit play when you're ready to check your work. So we said that some of these were out, but some of them were in. So this regular hexagon, I can just like click it right into place, and that's definitely more than 0 and less than 60. Circles, of course, you can rotate anywhere, and it's going to be right on top of itself. My parallelogram, I can actually do a full 180 rotation, and it would be right on top of itself again. And of course, my lovely star. My lovely star does rotate onto itself pretty quick here, more than 0 and less than 360. The others didn't work. For my isosceles trapezoid, I had to go full 360. That's not rotational symmetry. That's too much. For my scalene right triangle, again, I would have to rotate a full 360 degrees, so it doesn't have rotational symmetry. It has to be less than that. What about number 7? Do you think this shape has rotational symmetry? Hit pause, jot down your thoughts. Why or why not? Hit play to check your work. I said this has rotational symmetry, right? I could go 90 degrees and click it back into place, and another 90 back into place, another 90 back into place. Wow. So it has a lot of rotational symmetry, right? I could go 90 degrees, click it in once. I could go 180 degrees to click it in, or a full 270. I could go 3 clicks, like click, 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 and I would rotate it right onto itself. Awesome. So we've talked about reflectional symmetry. We've talked about rotational symmetry. Can a shape have both? Explain your thoughts. Hit pause. Write it down. Hit play when you're ready to check your work. Sorry. Clearly, I'm having some issues with my transitions here. Yes, a shape can have both reflectional and rotational symmetry. We've shown that our regular hexagons, our circles, our star, those both had reflectional and rotational symmetry. So yeah, we can do that. So you've identified transformations that can carry a figure onto itself. Reflectional and rotational symmetry are just properties of figures that we can reflect, that we can carry onto themselves by reflections and rotations. As always, I hope you found this helpful. I hope you found this useful. Pretty sure you found it entertaining and laughed at my expense a few times today. If you have questions or concerns, come talk to me. I'll see you guys soon. Bye.